Hello students, welcome back to our online class. Today we are going to discuss about the particle nature of light explained by Einstein. Next properties or characteristic properties of photons. Then explanation of photoelectric effect on the basis of quantum theory of light by Einstein, right? From the chapter dual nature of radiation and matter. Dual nature of radiation and matter, right? The chapter name is dual nature of radiation and matter. The topics we are going to discuss now are, first one, particle nature of light. Right, explained by Einstein. Or Einstein explanation. Next, characteristics of a photon. Next, explanation of Einstein's photoelectric equation. Right, so these are the topics in the chapter dual nature of radiation we are going to discuss now, right? So first we go for particle nature of light, okay, explained by Einstein, right? We know that there are various theories were proposed during 19th century by different scientists, right? All the theories are completely explained about the nature of the light. So there are various theories explained by different scientists during 19th century. So all the theories of light could completely explain about the nature of the light, right? One of the important theory of light is quantum theory of light. Quantum theory of light. Quantum theory of light, right? And it was explained by, or it was proposed by Max Planck. Right? So there are various theories like corpuscular theory. It was explained by Sir Isaac Newton. Wave theory. The wave theory was explained by Huygens. And next, electromagnetic theory. It was proposed by James Clerk Maxwell. And finally, quantum theory of light. It is one of the important theory of light. It was explained by Max Planck, right? According to Max Planck, the light energy or energy of light was emitted and absorbed not continuously. It is in multiples of discrete packets of energy. Okay, for example, let us consider a source of light. Suppose it emits light energy. The energy of the light emitted from the source is not continuously, according to Max Planck. So according to Max Planck, the light energy emitted from the source is not continuously, right? And also the energy of the light emitted from the source is absorbed by, suppose, any one of the medium. Okay, that light energy absorbed by the medium is also not continuously. It is in multiples of discrete packets of energy. Okay, 1 hnu, 2 hnu and 3 hnu, like that. Okay, so according to Max Planck, it was suggested that in his quantum theory of light, the suggestion is that the light energy was emitted and absorbed is not continuously. It is in multiples of discrete packets of energy. That is called quantum. That is called quantum, right? And this quanta cannot be subdivided in smaller parts. Okay, that is the quanta cannot be divided like this. Okay, cannot be divided or it cannot be splitted off, right? So, I mean, the light energy emitted from the source is not continuously. The light energy absorbed by the medium also not continuously, but it is in multiples of discrete packets of energy, that is called quanta. The energy associated with each quanta E is equal to NH nu. E is equal to NH nu, right? And one more thing, this quanta cannot be subdivided, cannot be divided into smaller parts. So these are the suggestions given by Max Planck in his quantum theory of light. Right? Later, Albert Einstein extended Max Planck idea. Okay? Einstein extended, okay, developed or reproposed the Max Planck's idea in the same quantum theory of light. And he was suggested that the light energy emitted from the source, cannot be spread out over the wavefronts. So these are wavefronts. So this is source of light, right? The source of light emits light energy. The light energy emitted from the source cannot be spread out over the wavefront, right? It is concentrated in small packets of energy. So according to Albert Einstein, the light energy emitted from the source cannot be spread out over the wavefront. It is concentrated in a small packets of energy. It is concentrated in a small packets of energy. It's called photon. Okay, so Albert Einstein extended Max Planck idea in quantum theory of light, and he was proposed that the light energy cannot be spread out over the wavefront and is concentrated in small packets of energy called photon. The energy associated with each photon is E is equal to h nu. Energy of quanta is equal to NH nu, right? Here H Planck's constant and nu is the frequency of the radiation. N number of photon, which is called quanta. The quanta cannot be subdivided into smaller parts. So these are the suggestions given by Max Planck. But according to Einstein, the energy of the light cannot be spread out over the wavefront. So these are the wavefront, right? And it is concentrated in small packets of energy. That is called photon, right? The energy of the photon is given by E is equal to h nu. Already I told h be the Planck's constant and nu is the frequency of the radiation. Right? And also Einstein was proposed that the light photon have a linear momentum. Because the light photon travels with the velocity of light. So definitely the photon possesses linear momentum, right? The linear momentum possessed by the photon is given by P is equal to E divided by C or h nu divided by C or h divided by lambda. The energy of each photon is E is equal to h nu. The linear momentum possessed by the photon is given by P is equal to E divided by C, where E energy of the photon and C velocity of light. We know that the velocity of light is 3 into 10 power plus 8 meter second power minus 1. Velocity of light 3 into 10 power plus 8 meter second power minus 1. Right. And H Planck's constant. The value of Planck's constant 6.626 into 10 power minus 34 joule second. Velocity of light 3 into 10 power plus 8 meter second power minus 1, and value of Planck's constant 6.626 into 10 power minus 34 joule second, and linear momentum of the photon is P is equal to E divided by C. So this is linear momentum expression in terms of energy of a photon, right? In terms of frequency of the radiation, the momentum of the photon is given by P is equal to h nu divided by C. And the momentum of the photon in terms of wavelength of the radiation, P is equal to h divided by lambda. Okay, so these are the expressions for the linear momentum of the photon, and this is energy of the photon. Right. So here the photon possesses both the energy and linear momentum. The photon possesses energy and momentum. So the photon is biggest like a particle. The photon is biggest as a particle, right? So these are the suggestions given by Albert Einstein. Albert Einstein, right? So this is particle nature of light explained by Einstein into quantum theory of light. So according to Albert Einstein, the energy of the photon is equal to h nu, and linear momentum of the photon p is equal to E divided by c, and h nu divided by c or h divided by lambda. So from this, Einstein was concluded that the photon is biggest as a particle. The photon is biggest as a particle, right? And the photons are the basic constituents of all the radiation. Okay, if the radiation, X radiation means the X radiation also consists of a photon. Okay, and suppose light radiation means the light radiation also consists of a photon. Gamma radiation also consists of a photon. Ultraviolet radiation, it is also consists of a photon. So the photon are the basic constituents of all the radiation, and it has some important characteristics. So some of the characteristics of a photon is listed out in our textbook. Characteristics of a photon or characteristic properties of photon. Right. So first characteristics, right? The photon of light of a frequency, suppose nu, and the corresponding wavelength lambda will have energy. Okay, the energy of the photon is given by E is equal to h nu, or E is equal to hc divided by lambda. Right? If any radiation having frequency nu and corresponding wavelength lambda, that radiation consists of a photon in it. The energy of the photon is given by E is equal to h nu, or E is equal to hc divided by lambda. We know that the velocity of light is given by the relation c is equal to nu lambda. The product of frequency of the radiation and the wavelength of the radiation gives the velocity of light or velocity of radiation. And velocity of radiation in free space is given by c is equal to nu lambda. Therefore, nu is equal to c divided by lambda. Nu is equal to c divided by lambda. Right? Just to replace nu into c divided by lambda, then we can get E is equal to hc divided by lambda. So this is the energy of the photon equation in terms of frequency of the radiation. If the frequency of the radiation is replaced by wavelength, that is lambda, then this equation becomes hc divided by lambda. So the photons of light of frequency nu and wavelength lambda will have energy. It is given by E is equal to h nu, or E is equal to hc divided by lambda. H Planck constant, nu frequency of the radiation, and c velocity of light, and lambda wavelength of the radiation. So this is one of the characteristics of photon. Right? And next, the energy of the photon is determined by the frequency of the radiation. The energy of the radiation is determined or can be determined by using the frequency of the radiation, because energy of the photon is given by the relation E is equal to h nu. H is a Planck's constant. This is constant. So the energy of the radiation is directly proportional to frequency of the radiation. If the frequency of the radiation is more, the energy of the photon in that radiation also more. So the energy of the photon can be determined from the frequency of the radiation. But the energy of the photon cannot be determined by using the intensity of the radiation. Okay, by using intensity of the radiation, because there is no relation between the intensity of the radiation and the energy of the photon or energy of a single photon in that radiation, right? But actually there is a relation between energy of the radiation and the intensity of the radiation. The intensity is nothing but energy per unit area, or power per unit time per unit area. This is intensity equation in terms of energy. The unit of intensity is watt meter power minus 2. Watt meter power minus 2. Right. So this is intensity unit. So this is a relation between intensity of the radiation and the energy of the radiation. But there is no relation between intensity of the radiation and the energy of individual photons of the radiation. Energy of individual photons of radiation, there is no relation. But there is a relation between intensity of the radiation and the energy of the radiation. Energy of the radiation. So that is why the energy of the photon can be determined only from the frequency of the incident radiation, but cannot be determined from its intensity. From its intensity. Why? Because the intensity of the there is no relation between intensity of the radiation and energy of the individual photons in the radiation. Individual photons in the radiation. So this is second characteristics of a photon. Right. And third, the photon can travel with the velocity of light. Where? In free space. The photon can travel with the velocity of light. That is of the order of 10 power plus 8 meter second power minus 1. The photon can travel with the velocity of light. Velocity of light. So it possesses a linear momentum. Already I told. The linear momentum of the photon is P is equal to h nu divided by C. Linear momentum P is equal to h nu divided by C, or E divided by C, or h divided by lambda. Right? Already I told. The linear momentum of the photon P is equal to h nu divided by C, or P is equal to E divided by C, or P is equal to h divided by lambda. Right? The photon is travels with the speed of light. It is of the order of 3 into 10 power plus 8 meter second power minus 1. So it possesses a linear momentum. The magnitude of linear momentum is given by the relation P is equal to h nu divided by C, or P is equal to E divided by C, or P is equal to h divided by lambda. H divided by lambda. Right. And next characteristic property of a photon is that the photon is electrically neutral. Electrically neutral. Electrically neutral means they are chargeless. The photons are chargeless. That is, they are electrically neutral. So the photons cannot be deflected by electric field and magnetic field. The photons cannot be deflected by electric field and magnetic field. Why? Because the photons are electrically neutral. They are chargeless. Only charged particle alone deflected by electric field and magnetic field. But the photons are being chargeless, that is electrically neutral. They are not deflected by electric field and magnetic field. Not deflected by electric field and magnetic field. Suppose if the photon is moving along a positive x-axis direction, suppose in this region electric field is exist, right? So even though the electric field is exist in this region, okay, the photon never deviate from its original path. It always goes along the straight line path. Okay, because the photon are chargeless. So it cannot be deflected by electric field or otherwise magnetic field. Right? So the photons are electrically neutral, that is chargeless. So they are not deflected by electric field and magnetic field. Right? And next, when the photon interacts with any one of the matter, for example, the electron in the metal. So there is a metal which consists of large number of electrons. Suppose a photon is interact with matter. Matter means suppose the electron in the metal. Right? The total energy of the photon and the total linear momentum of the photon, and total angular momentum of the photon is conserved. Right? Whenever the photon interacts with matter, that is, suppose the electron in the metal, the total energy, total linear momentum, total angular momentums are conserved. Right? Because during the interaction, the photon may be absorbed by the matter or absorbed by the electron in the metal. Or during the interaction, a new photon may be produced. But the number of photons cannot be conserved. Right? So this is very important characteristics of photon. Right? So whenever photon interacts with the matter, the total energy, total linear momentum and total angular momentum are conserved, but the total number of photons cannot be conserved. Total number of photon cannot be conserved because when the photon is interacts with the matter, the photon may be absorbed by matter or a new photon may be produced. A new photon may be produced. So that is why these three quantities are conserved, but the number of photons cannot be conserved. So these are the properties of a photon. So once again I repeat all the characteristic properties of a photon one by one. So first one, the photons of light of frequency nu and wavelength lambda will have energy. It is given by the relation E is equal to h nu or E is equal to hc divided by lambda. E is equal to hc divided by lambda. Second, the energy of the photon can be determined from the frequency of the radiation, but it cannot be intensity of the radiation. Not be intensity of the radiation. Right? Reason, there is no physical relation between the intensity of the radiation and energy of the single photon of the radiation. Single photons of the radiation, right? And third, the photon travels with the velocity of light, so it must possess a linear momentum. The linear momentum magnitude can be calculated by using the formula P is equal to h nu divided by c, or P is equal to E divided by c, or P is equal to h divided by lambda, right? And next one, the photons are being chargeless. They are electrically neutral. So they are not deflected by electric field and magnetic field. If the photon is subjected in the electric field and the magnetic field, it never deflected from its original path. Right? The big reason, chargeless. They are electrically neutral. Right? And the final one, when the photon interacts with the matter, the total energy, total linear momentum and total angular momentum are always conserved, but the total number of photons may not be conserved. Right? The reason, while or during the interaction, the photon may be completely absorbed by matter or a new photon may be produced. New photon may be produced. So these are characteristics of photon. Characteristics of photon. Einstein photoelectric equation. Einstein's photoelectric equation, or explanation of Einstein photoelectric equation. Einstein photoelectric equation, right? So Einstein explained the photoelectric effect on the basis of a quantum theory of radiation. On the basis of quantum theory of radiation, right? According to him, suppose let us consider a single photon of energy h nu in the radiation is incident on a metal surface. Right? So this is a photon whose energy is h nu and which is instant on the metal surface. Right? When the photon is instant on the metal surface, the entire energy of the photon is absorbed by the electron in the metal surface, or electron in the metal. Electron in the metal. Right? It is completely absorbed by the electron in the metal. Electron in the metal. Right? So whenever the electron absorbs the energy of from the energy of the instant photon, then the electron comes out or ejected from the metal. The electron is ejected from the metal, right? So here the total energy of the instant photon actually here used up in two ways, right? A part of the energy of the instant photon is used to extract the electron from the metal surface. Extract the electron from the metal surface, right? And the remaining part of the energy of the instant photon is completely converted into kinetic energy of the electron. Kinetic energy of the electron, right? Here, h nu be the energy of the photon in the given radiation, which is instant on the metal surface. When the photon is instant on the metal surface, the entire energy of the photon is absorbed by the electron in the metal surface. Electron in the metal surface. Results, there is a ejection of electron from the metal surface. Ejection of electron from the metal surface. Right? So during this process, the energy of the photon is used up in two ways. That is, one part of the energy of the photon is used up to extract the electron from the metal surface, which is called photoelectric work function of the metal. Photoelectric work function. Photoelectric work function. What is meant by photoelectric work function? The minimum amount of energy is required to liberate the electron from the metal surface. Liberate the electron from the metal surface is called photoelectric work function. Photoelectric work function or photoelectric work function of the metal. Photoelectric work function of the metal. It is denoted by pi naught. The photoelectric work function of the metal is denoted by pi naught. Right. And the remaining part of the energy of the incident photon is converted into kinetic energy of the emitted electron. Kinetic energy of the emitted electron. Right. Here kinetic energy of the emitted electron is denoted by or given by of mv square. H nu, energy of the instant photon. Okay. From this total energy of the photon, a part of its energy is used to extract the electron from the metal surface, and the remaining part of the energy is converted into kinetic energy of the emitted electron. Kinetic energy of the emitted electron. Okay, that is the total energy of the photon is h nu, which is used up in two ways. One part is nothing but the photoelectric work function of the metal, and the remaining part the kinetic energy of the emitted electron. Kinetic energy of the emitted electron. So nu, frequency of the incident radiation. H, Planck's constant. H into nu is called energy of the photon. Energy of the photon is equal to pi naught work function of the photometal. Right? One of the part of the incident photon is used to extract the electron from the metal surface, because the electrons are tightly bound to the nucleus. The electrons are tightly bound to the nucleus. So energy must be needed to extract the electron from the metal surface. So that energy required is called photoelectric work function of the metal. And the remaining part of the energy is converted into kinetic energy of the emitted electron. Kinetic energy of the emitted electron. So h nu, energy of the instant photon, pi naught, photoelectric work function of the metal. Already told what is meant by photoelectric work function of the metal. The minimum energy required to liberate the electron from the metal surface is called photoelectric work function of the metal. And the remaining energy becomes kinetic energy of the emitted electron. Kinetic energy of the emitted electron. Where here m is mass of the electron and v the velocity of the electron. The velocity of the electron. While the electron comes out from the metal surface, it possesses some velocity. Okay, it is denoted by v, and mass of the electron is denoted by m. So of m v square is the kinetic energy of the emitted electron. So sum of the kinetic energy of the emitted electron and the photoelectric work function of the metal gives the total energy of the instant photon. The total energy of the instant photon. Right. Suppose if the frequency of the, here nu be the frequency of the instant radiation. If the frequency of the instant radiation is gradually reduced, what will happen? If the frequency of the instant radiation is gradually reduced, the electron now also comes out from the metal surface, but the velocity and as well as the kinetic energy of the electron is also decreases. Right? When the frequency of the instant radiation is reduced or decreased continuously, and velocity of the emitted electron and also the kinetic energy of the emitted electron also reduced. Right? At one particular frequency of the instant radiation, that is, suppose the frequency of the instant radiation is nu naught, then the corresponding photon energy is h nu naught. H nu naught, right, is instant on this metal surface. Actually, electron is comes out from the metal surface, but with zero kinetic energy. With zero kinetic energy. If the frequency of the instant radiation is nu naught and the corresponding energy of the photon is h nu naught, which is instant on the metal surface, the electron comes out from the metal surface, but with zero kinetic energy. With zero kinetic energy. Suppose if the frequency of the radiation is equal to nu naught, then the kinetic energy of the emitted photoelectron becomes zero. The kinetic energy of the emitted photoelectron becomes zero. So substitute nu equal to nu naught and of mv square equal to 0 in this equation. Then this equation becomes h nu naught plus is equal to pi naught and of mv square is 0. Of mv square is 0. right? Therefore, h nu naught is equal to pi naught. So work function, that is the photoelectric work function of the metal is given by pi naught is equal to h nu naught, right? Here nu naught is called threshold frequency. Threshold frequency. What is meant by threshold frequency? The minimum frequency of the incident radiation below which no photoelectric emission takes place, above which the photoelectrons are emitted, right? The minimum frequency of the incident radiation above which photoelectrons are emitted, below which no photoelectrons are emitted. So such a frequency or minimum frequency is called threshold frequency. If the radiation, frequency of the incident radiation on the metal surface is equal to the threshold frequency of the photometal, the photoelectron comes out from the metal surface but with zero kinetic energy. Right? By using that condition, we can calculate what is the photoelectric work function of the metal by using the relation. That is pi naught is equal to h nu naught. Right? Now, substitute pi naught is equal to h nu naught in this equation. Then this equation becomes h nu is equal to h nu naught plus of mv square. Right, h nu is equal to h nu naught plus of mv square, or h nu is equal to pi naught plus of mv square. So this is in terms of photoelectric work function, and this is in terms of threshold frequency. Right. Suppose during photoelectric effect, the electron does not undergo any internal collision. Okay, that is, if there is no internal collision during photoelectric effect, the electrons are ejected with the maximum kinetic energy. The electrons ejected from maximum kinetic. Suppose the energy of the incident photon, for example, 100 joule. For example, so 100 joule of energy of a photon is incident on the metal surface. Right. The minimum energy required to eject the electron from the metal surface, suppose 25 joule, right? So this is called photoelectric work function of the metal, right? So photoelectric work function is 25 joule, right? If there is no internal collision during this process, the remaining energy, that is 100 joule minus 25 joule, that is equal to 75 joule. The 75 joule amount of energy is completely converted into the kinetic energy of the electron. So that kinetic energy is called maximum kinetic energy of the emitted electron. That is of mv square maximum or k maximum. Right? If there is no internal collision is involved, the electrons are ejected with the maximum kinetic energy. Right? Then this equation can also be written as h nu is equal to pi naught plus of mv square maximum. Right. This is Einstein's photoelectric equation. Einstein photoelectric equation. H nu is equal to pi naught plus of mv square maximum. This condition or this equation is only applicable for if there is no internal collision is involved by electron during photoelectric effect, right? Otherwise, this equation should be h nu is equal to pi naught plus of mv square, or otherwise h nu is equal to h nu naught plus of mv square. But the ancient photoelectric equation is h nu is equal to pi naught plus of mv square maximum. Ancient photoelectric equation is h nu is equal to pi naught plus of mv square maximum. Maximum, that is maximum velocity of the emitted electron. Of mv square maximum kinetic energy of the emitted electrons. Pi naught, work function of the metal. And h nu, energy of the instant photon. Or h nu is equal to h nu naught plus of mv square maximum. So this is also Einstein photoelectric equation. Einstein photoelectric equation, right? Here pi naught is equal to h nu naught, and maximum kinetic energy of the emitted photoelectron is of mv square maximum. Of mv square maximum, right? Okay, here of mv square maximum or k maximum is equal to, this is k maximum, is equal to h nu minus h nu naught. If h nu naught is taken left hand side, and this equation becomes k maximum, that is instead of mv square maximum I am writing k maximum, which is equal to h nu minus h nu naught, minus h nu naught, right? Suppose for the different frequency of the incident radiation, here h Planck's constant and nu is a threshold frequency. These two values are constant. And here nu is the frequency of the radiation. If the frequency of the radiation is changes, automatically the kinetic energy of the emitted electron value also changes, right? So taking the different values of frequencies and along the x-axis, and the corresponding kinetic energy of the emitted electron along the y-axis, by drawing a graph, by taking the frequency of the radiation along the x-axis and the kinetic energy of the emitted electron along the y-axis, we can get a graph like this. Right, that is the nature of the graph is a straight line. When we draw a graph by taking the frequency of the radiation along the x-axis and the kinetic energy along the y-axis, the nature of the graph is a straight line. The nature of the graph is straight line, right? And the slope of this line gives Planck's constant. The slope of the line gives Planck's constant, right? Here the x-intercept is equal to the threshold frequency of the incident radiation. X-intercept is the threshold frequency of the incident radiation, right? And y-intercept is nothing but work function, that is photoelectric work function of the metal, that is h nu naught. So y-intercept of the graph which is drawn between the frequency of the radiation and the kinetic energy gives the photoelectric work function of the metal, that is pi naught is equal to h nu naught. Here x-intercept is nothing but the threshold frequency, and slope of the line gives Planck's constant. Slope of the line gives Planck's constant. Okay, at one particular frequency of the incident radiation, the kinetic energy of the emitted electron is a maximum. The kinetic energy of the emitted electron is maximum, right? Here, this is the frequency of the incident radiation. Among this energy, a part of the energy is used as photoelectric work function of the metal, and the remaining part of the energy becomes the maximum kinetic energy of the emitted electron. Maximum kinetic energy of the emitted electron. So from this graph, it is clear that the nature of the graph drawn between frequency of the incident radiation and the kinetic energy of the emitted photoelectron is a straight line, and the slope of the straight line gives Planck's constant, and x-intercept is threshold frequency of the incident radiation or a threshold frequency, and y-intercept is photoelectric work function of the metal. Photoelectric work function of the metal, right? So these are the theoretical explanation given by Einstein on the basis of quantum theory of radiation. Theoretical suggestion. So far, Albert Einstein gave a suggestion regarding photoelectric effect theoretically, but it was experimentally explained and verified by Millikan. Einstein photoelectric equation was experimentally verified by Millikan. Right, already I told Einstein photoelectric equation was experimentally verified by Millikan. Photoelectric effect was discovered by Heinrich Hertz. It was theoretically explained on the basis of quantum theory of radiation by Einstein. And Einstein photoelectric equation was experimentally verified by Millikan. H.A. Millikan. Right. So Millikan conducted several experiments by using different metals, by using different alkali metals. like cesium, potassium, sodium and calcium, right? So H.M. Milligan, in order to verify Einstein photoelectric equation, he was conducted several experiments by using different alkali metals like cesium, potassium, sodium and calcium. And after performing those experiments, he was found that the slope of these lines gives Planck's constant, and which is independent of the nature of the metal. If calcium metal is used in the photoelectric effect, photoelectric effect experiment, the slope of the line gives Planck's constant. If sodium metal is used, the slope of the line gives Planck's constant. Alright, so potassium or cesium metals are used, the slope value is always Planck's constant. So Milligan was experimentally found that by using different metal, the slope of the line obtained in the frequency maximum kinetic energy graph gives Planck's constant. The value of Planck's constant is 6.626 into 10 power minus 34 Joule second. And also the Planck's constant value, Milligan also determined the value of Planck's constant. The value of Planck's constant is 6.626 into 10 power minus 34 Joule second. And also Milligan was determined the photoelectric work function of the different metals, that is different alkali metals, cesium, potassium, sodium and calcium, right? So Milligan measured the photoelectric work function of cesium metal experimentally. That value is minus 2.14 electron volt. Electron volt is one of the unit of energy, right? For potassium metal, the photoelectric work function value is minus 2.30 electron volt. And for sodium metal, photoelectric work function is minus 2.75 electron volt. For calcium alkali metal, the photoelectric work function is minus 3.20 electron volt. So Milligan measured the photoelectric work function of different alkali metals experimentally. Okay, that values are here listed out here. Minus 2.14 electron volt, minus 2.30 electron volt, minus 2.75 electron volt, minus 3.20 electron volt for the metals like cesium, potassium, sodium and calcium. For all the metals, even different metals are used in that experiment, the nature of the graph drawn between frequency of the radiation and the kinetic energy is always a straight line. The slope of all the line gives Planck's constant. Okay, Milligan measured the value of Planck's constant experimentally. The value obtained is 6.626 into 10 power minus 34 Joule second, right? And also he was found that the slope of the line is independent of the nature of the metal. The slope of the line is independent of nature of the metal. So Milligan was the first one verified ancient photoelectric equation experimentally. Right, my dear students, so far we discussed about the particle nature of light, that is Einstein explanation, and next characteristic properties of a photon, and next Einstein photoelectric equation. So in this topic we discussed about Einstein explanation. That is, according to Albert Einstein, the light energy emitted from the source not spread out over the wavefront. It is concentrated in small packets of energy called photon. The energy of the photon is E is equal to h nu. The photon possesses a linear momentum. Its magnitude is given by P is equal to E divided by C, or P is equal to h nu divided by C, or P is equal to h divided by lambda, right? And finally, Albert Einstein was concluded that the photon possesses energy and momentum, so it behaves as a particle. Right? So this is Einstein explanation, that is particle nature of light. Next, characteristics of a photon. What are the characteristics? First one, if the radiation of a frequency nu and wavelength lambda, the radiation consists of a photon. The energy of the photon is given by E is equal to h nu, or E is equal to hc divided by lambda. Second, the energy of the photon is determined by the frequency of the radiation. not by intensity of the radiation. Not by intensity of the radiation, right? And third, the light travels with, photon travels with the velocity of light. So it possesses a linear momentum. It is given by P is equal to E divided by C, or P is equal to H nu divided by C, or P is equal to H divided by lambda. H divided by lambda, right? And the next one, the photons are electrically neutral. So they are not deflected by electric field and magnetic field. Final one, when the photon is interacts with the matter, the total energy of the photon and total linear momentum and total angular momentums are conserved, but the total number of photons cannot be conserved. Total number of photon cannot be conserved, right? And next to Albert Einstein explained the photoelectric effect on the basis of quantum theory of radiation, and he derived a simple expression is called, or equation is called, Einstein photoelectric equation. The Einstein photoelectric equation is H nu is equal to pi naught plus half mv square maximum. Pi naught is equal to half mv square maximum. This is Einstein photoelectric equation. It was experimentally verified by Millikan. So he was conducted several experiments by using different alkali metal. After performing that experiments, he was found that the value of slope of the line is independent of nature of the metal. And also he was determined the value of Planck's constant and the value of photoelectric work function of different alkali metals experimentally, right? So Einstein photoelectric equation was experimentally verified by Millikan, right? Thank you, students. We will see in the next class.